I am Wan Jun Son, and this presentation will introduce the advancement in the development of the prototype of a fully implantable bidirectional brain-computer interface. For a person with spinal cord injury, the restoration of functional independence can be sought with using assistive devices. More recently, wearable robots and bionic suits are becoming available in the market to assist these people to restore walking. Here is a person with a lower limb paralysis getting help from a therapist to be loaded onto a robotic exoskeleton from ExoBionic to be able to walk. But the first step has to be triggered by the therapist, and the subsequent steps by moving the body to a lateral target zone. As fascinating as it is, it lacks a critical component, the ability to freely issue a voluntary motor command and the sensory feedback from walking. In the context of walking, a BCI recognizes the motor intent of a user through the brain signal to operate neuroprosthetics. For people suffering from a severe neurological impairment, the technology has shown considerable promise to bypass the damaged spinal cord by decoding motor intentions, as previously demonstrated in our lab about how EEG signal can operate the robotic exoskeleton. While much BCI research has been on the control of the robotic limb, there has been little work on how to provide sensory feedback to the patients. The lack of somatosensation causes a severe deficit in motor control. If you think about how we walk, we always know where the legs are, how fast they're moving, and on what they're stepping, which are not available to persons wearing prostheses. Therefore, electrically stimulating the sensory cortex to artificially evoke tactile and proprioceptive precepts can be a promising approach to restore sensation during walking and complete the closed-loop bidirectional BCI. With the recognition of the need, we envision this fully implantable BD-BCI system. This illustrates a hypothetical scenario where a person with a cervical spinal cord injury is implanted with a BCI system in the skull and the chest connected by the tunneling cable to bypass the damaged sensory motor pathway. A subdurally implanted ECOG electrodes, which provides excellent spatial temporal resolution and SNR, are mapped to the sensory motor fields relevant to walking. The skull unit will amplify, multiplex, and digitize the motor ECOG signal and pass them to the chest wall unit, which sends command to the end effector wirelessly. The movement of the end effector will trigger the artificial sensory stimulation from the chest wall unit to send current pulses back to the sensory ECOG grids to elicit artificial somatosensation of the movement. Toward this vision, we already developed and tested a benchtop of fully implantable unidirectional BCI system that can decode motor commands from ECOG signals. The objective of the study is to first develop a prototype benchtop system for the proposed fully implantable BD-BCI system, which includes electrocortical stimulator, as a step toward the envisioned fully implantable BD-BCI system, and secondly, to demonstrate a safe electrocortical stimulation method which integrates into the benchtop system. To sum up the objectives, we aimed at developing the BD-BCI via integration of the unidirectional BCI system with a stimulation circuit, and it is necessary to have a precise stimulation operating concurrently with the motor decoding while keeping the small footprint. Furthermore, it is specifically important for stimulation in the chronically interfaced electrode to provide active charge balancing in order not to induce irreversible reaction that can lead to electrode degradation and tissue damage. We develop a customized stimulator in order to elicit artificial sensation. The design aimed at achieving a maximum stimulation current of 50 mA to be delivered across 1 kΩ load. Therefore, a supply voltage as high as 15 volts is required. A current controlled biphasic square pulse stimulation is implemented with the H-bridge, driven by the current source, controlled by the digital rheostat. The system can deliver a stimulation with a pulse frequency up to 1 kHz, pulse width resolution of 10 nanosecond, and arbitrary train duration. Two 16:1 analog multiplexers select channels in the ECOG grids for bipolar stimulation. The measured feedback voltage is amplified and digitally converted to be read by the ADC pins of the microcontroller. This is a schematic of the active charge balancing circuit to prevent accumulation of charges at the electrodes. The increased voltage at the measurement electrodes activates the adaptive removal of residual charges by pulse width modulated corrections. Specifically, the sample voltage at each pulse cycle will be used as a feedback signal to adjust the anodic and cathodic pulses width of the immediate next pulse cycle, depending on the level of measured voltage. In the right box, you see the ECOG grid that is placed on phantom brain tissue. The dipole channels in 6x2 ECOG grid are stimulated bipolarly. The charge accumulation was tracked in the neighboring electrodes from the stimulation pair. The reference voltage was defined for the most distant electrode in the grid. In C, a binary state machine modulating the pulse width of the output stimulation was implemented to test one simple case of active charge balancing. It is basically if the measured voltage exceeds a certain amount of voltage, the cathodic intensive pulse are activated to neutralize the voltage. The charge balancing is tested by first an intentional buildup of residual charges at the measuring electrodes and activating the active charge balancing circuit to assess the removal of the accumulated charges. The stimulator circuit was successfully implemented on the printed circuit board, which integrates the stimulator and the existing BCI system. The output stimulation generated asymmetric biphasic square pulses, which are parameter controlled in the charge balancing experiment. The dotted box denotes the corresponding units in the fully implantable BD-BCI system. The following figures are the result of the charge balancing experiment. A shows a transient voltage response at the measurement electrode to the switching of the pulse output profile without the charge balancing mechanism. This is to demonstrate the effect of the shape of the waveform in the biphasic pulse stimulation over time. So without charge balancing, the 12:1 anodic versus cathodic pulse resulted in a steady-state positive potential. An abrupt switch to 1:12 anodic versus cathodic pulse causes the transient reversal of the steady-state voltage to negative, as expected. A B shows the effect of the charge balancing. When the charge balancing is off, the accumulation of charge at the electrode by 12:1 waveform is reflected in the steady-state voltage of 0.315 volts, whereas it was nearly 0 volts when the charge balancing mechanism was engaged. In panel B, 900 sample data points for each conditions are shown to contrast the steady-state voltage between the two conditions. As a conclusion of the study, the current study achieves a step toward a fully implantable BD-BCI by integrating a prototype artificial sensory stimulator into the existing BCI system. The study also tested the feasibility of an artificial stimulator equipped with a pulse width modulated active charge balancing. The study demonstrated that the active charge balancing method is capable of effectively removing the residual charges on an electrode to achieve the charge neutrality to prevent the mechanism from damaging tissue and the electrodes. The effect of stimulation artifact on the performance of the simultaneous BCI motor decoding was not assessed as a limitation of the study. However, it is expected that the techniques to suppress the stimulation artifacts will mediate the problem. We want to thank NSF for supporting the study and all the people who contributed to the study across the 3 campuses. Thank you very much.